Welcome. Today we're going to look at pulse wave ultrasound parameters. So waves produced by ultrasound transducers may either be pulse wave ultrasound, that is an ultrasound that is generated through short bursts of pulses, like when we're discussing about the components and the function of each component. Talk about how that several thousand, about 10,000 bursts of voltage hits the piezoelectric crystals, which generates ultrasound waves. Those waves actually are in bursts, but there are two waveform produced by ultrasound transducer. So it's either pulse wave ultrasound or continuous wave. Continuous wave cannot produce images. A transducer working in continuous wave mode always have two crystals. One group of crystals for transmitting ultrasound waves, another group of crystals for echo reception. The transmitted waves have uniform amplitude and frequency. The duty factor of the continuous wave is 1. It's always, in other words, always transmitting. So they are already dedicated piezoelectric crystals that generate ultrasound waves continuously, not in bursts. And there are also dedicated piezoelectric crystals that are dedicated to listening to the echoes, unlike in the other pulse wave where the transducer will generate and listen. So that's why I said earlier in the other class that the transducer speaks and listens. So in pulse wave, the same crystal speaks and the same crystal keeps quiet to listen. But it's not so with continuous wave. Continuous wave have dedicated crystals for each function. So pulse wave ultrasound is common in all diagnostic grayscale ultrasound images, in color Doppler and pulse wave Doppler, except for continuous wave Doppler. For real-time scanning and any other type of ultrasound image display, that is, you can find that in A mode, M mode, B mode, the system must be operating in pulse wave ultrasound mode in order to construct an image on a display. So with pulse wave ultrasound, an ultrasound pulse is not continuously generated. Instead, a transducer operated in the pulse mode uses the same crystal to transmit waves and to receive echo, like I said earlier. Pulse transducer transmit ultrasound in series of short pulses. Between successive pulses, the ultrasound is in reception mode, receiving or listening to the returning echo. That's to say, an ultrasound pulse is emitted, which is known as one time or talking time, and then there is a pause before next pulse is emitted. So it's just like tip, 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 tip. So the generation or transmission has intervals. During this pause, the transducer is receiving the reflection from the tissue, which is known as listening time or off time. So you will have the on time and off time. The crystal emits and receives signal in alternating fashion, with 1% of the time allotted to pulse production and 99% to listening time or off time. In pulse wave ultrasound, each ultrasound pulse consists of a collection of 2 to 3 individual wave cycles. The pulse move as one containing 2 to 3 cycles. So you can liken that, you can imagine that this explanation in maybe the locomotive train, where several cars are attached to each other at certain intervals. So they are joined at the point where they are joined. You call those points the on time, then the cars are the off time. So remember that the on time is just 1%, the off time is 99%. So it listens more than it speaks. In pulse wave ultrasound, the pulse must have a beginning and an end, otherwise it will be a continuous wave. So we're going to look at 5 parameters used in this to describe pulse wave ultrasound, and these are pulse repetition frequency, pulse repetition period, pulse duration, spatial pulse length, and duty factor. All these are very important and are actually working in your machine without your express knowledge, or without you having to think about it. And if you are a student preparing for exam, all these are very important for you to take note of. So let's look at pulse repetitive frequency, PRF. And this is defined as the number of ultrasound pulses transmitted per second. The rate a pulse transducer is electrically activated to produce and transmit an ultrasound pulse wave is known as the PRF. So since all the ultrasound images are created using a series of pulses, the PRF is an important concept. It is also analogous to frequency, typically ranges from 1000 to 10,000 kilohertz. The unit is measured in hertz, is determined by the sound source, and can be changed by the sonographer. The PRF is determined by the pulsar. Remember the pulsar in the component or machine component? That's where it is determined. And you can actually have a knob on your machine that can adjust the PRF. But let's go on and we'll see that. The PRF is limited by the depth of the field. Since an ultrasound system must wait for all the echoes to return before transmitting another pulse, the deeper the depth of the field, the lower the maximum PRF must be set, so that it will accommodate distant echoes. Because if it's not set lower, you may lose some echoes, especially if you are doing a color Doppler. But we'll see how it applies as we go. The PRF is inversely proportional to the depth of the field. The PRF is a key factor in many ultrasound processes, such as frame rate and Doppler. Do not confuse it with frequency. The two are unrelated. So the equation for PRF is inverse PRP. PRP is pulse repetition period, which is measured in milliseconds. PRF, pulse repetitive frequency, it is the reciprocal of PROP and imaging depth. So this is a test question for you to help you understand how to apply, because you remember what we say is the reciprocal of PROP. So you apply that in the question and you should be able to understand what it is. So pulse repetitive period, PRP, is the time from the start of one pulse to the start of the next pulse. It includes both the on time and the off time. It is analogous to period. Unit is millisecond. Is determined by the sound source only, and can be changed by the sono or the technician. PRP is reciprocal of PRF, so in other words, they are inversely proportional to one another. When the operator adjusts the depths of view, he actually alters the receiving time. So the depth of view, that's the penetration, is directly related to the PRP and inversely related to PRF. So every time you adjust your depth, you have done something to your penetration and your PRP. So the equation for PRP is inverse. Of course, remember PRF is inverse PRP because they are inversely proportional. So it's vice versa. So the first is from the above from the above equation, we can see the PRP is composed of two time interval. The first is the pulse duration. First, the pulse duration, PD, the time during which the transducer is generating ultrasound. It is also called the on time. So pulse duration time is the on time. That is when the transducer is actually transmitting ultrasound. Remember, it transmits over 3 cycles of frequency per second. The second is the reception time, that's the off time, the time during which the sound transmission is off and the system is listening for echo. In other words, it's receiving. The PD and the reception time comprise of PRP. So PD, reception time, makes up the PRP. The reception time varies with the imaging depth, of course. The reception time must be long enough to wait for any echo returning from the depth of the field. If the depth of the field is deep, the reception time must be long. If the depth of the field is shallow, then the reception time can be reduced. This of course affects the PRF, since PRF is inversely proportional to PRP. A deep field of view requires a lower PRF in order to keep the PRP long. The opposite is true for a shallow depth. So you want to keep the PRP long, you need a lower PRF. So we can see that the maximum PRF for an ultrasound system is limited by the depth of field. The greater the imaging depth, the longer the time it takes echo to return to the transducer, and the longer the PRP and the lower the PRF would be. In current ultrasound system, the PRF automatically adjusts when the operator selects imaging depth. Shallower display depths permits a higher PRF to be used, while deeper display depth reduces the maximum PRF. So in some older machines, there are buttons there are knobs rather to adjust some of these parameters. But in newer and latest machines, You don't necessarily have to worry about that. So the moment you strike your zoom button, you actually automatically adjust some of these things. In fact, the machine does it for you when you strike that button. So let's look at pause duration. This is the time it takes for a pause to occur. Remember, pause PD is the on time. It is the time from the start of a pause to the end of that pause. It is only the time that the pause is on. PD is very short. Each ultrasound consists of a few cycles of ultrasound. Typically, there are only 2 to 3 cycles of sounds in each pause. So that tip, 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 tip. In fact, if you put your probe to your ear, you hear tick, 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 tick. So there is a quick succession of duration. So PD is just when it's on only. The unit is microsecond, determined by the sound source only, and the sonographer cannot change this particular parameter. So the equation for PD, pulse duration time, is the number of cycles per pulse times time. So you want to determine the pulse duration, you know the number of cycles, which is 2 to 3 times time. You get it. Since period is T, it is the reciprocal of frequency, yeah? The formula can also be written as PD, also number of cycles over frequency. If the pulse is produced by a 5 megahertz transducer, the PD will be what? We know frequency, we know cycle, we're taking 3 cycles per second. And PD is 0.6 microsecond based on that formula. So thus, if the period and the time of cycle in the pulse are increased, PD increases. But if the frequency increases, the PD is decreased. So PD is directly proportional to period. PD is directly proportional to the number of cycles per pulse. PD is inversely proportional to frequency. Take notes. You definitely will be asked this kind of questions in the exam. So an increase in the period or number of cycles per pulse will increase the PD. A decrease in either will shorten the PD. Most pulses contain consistent number of cycles. Sound frequency has the greatest effect on PD. The shortest pulses are produced by high frequency transducer, of course. Thus, the period of high frequency ultrasound is shorter than the period of low frequency ultrasound. So you can also use this example to test what you've understood based on the formulas we've given above. And a quick walk that we do here. So let's go to spatial pulse length. This is the length or the distance that a pulse occupies. It is the length or distance from the start of a pulse to the end of a pulse. SPL, which is spatial pulse length, often starts simply as pulse. It is also just stated pulse length, basically. And it's analogous to wavelength. The unit is centimeter or millimeter. And it usually will range from 0.1 to 1 mm. It's determined by sound source and a medium. So the operator cannot adjust this. SPL will decrease when the wavelength decrease or frequency is increased. there are fewer cycles in the pulse. So the equation for spatial pulse length will be number of cycles over the wavelength. Multiplied by the wavelength. Since we already know that wavelength is equals to speed of light over frequency, we can now apply that to say number of cycles times speed of light over speed of sound over frequency. Speed of sound. So for soft tissue, we already know the constant value for soft tissue, which is 1.54 mm per microsecond. So it will be number of cycles times that value over frequency. So when you do this exercise, you're able to calculate SPL. I think you should work it out. So SPL has clinical importance, which is the primary factor which determines the axial resolution of an image, thereby image quality. So SPL is actually all about image quality, and that's why it's important we calculate it and understand how it works. Good axial resolution requires short pulses. That is why you have higher frequency probes producing good quality images, and lower frequency probes have reduced because of their axial resolution. So remember that as a sonographer, using a high frequency transducer is the best way you can ensure that you have the shortest spatial pulse length and the best axial resolution if penetration is not necessary. So let's do a quick peek on axial resolution. Axial resolution refers to how close two reflectors can be to one another and still be distinguished as separate reflectors along the beam. The simple formula for that will be SPL divided by 2. As the length of the pulse is decreased, the axial resolution improves, which is desirable, of course. Also, what's the relationship? SPL is directly proportional to wavelength. SPL is directly proportional to the number of cycles in a pulse. SPL is inversely proportional to frequency. As the frequency is increased from 5 megahertz to 7, the SPL will decrease due to decreased wavelength. Axial resolution will improve. That is for better quality. So in the next video, we're going to be looking at duty factor, duty cycle, and all that it pertains. So you take your time to do some of this exercise within the video, and make sure you take note of all the formulas. You don't need to derive them, just know them for exam purposes. All right, thank you. See you on the next video. Don't forget to like the video, subscribe to our channel so that we can bring more of this to you. Thanks a lot.